Now let's kick it up a notch and do an example with an exponential, of course. Those are fun. So let's just make a note as we do this real quick that if z was equal to e to the 7x, then the derivative of z with respect to x would be 7e to the 7x because of chain rule, right? Just a little reminder, I guess I shouldn't say note, I should just say recall, just a little for our own benefit, right? All right, now why am I doing that? Well, because I wanted to remind us for the sake of this, because if I want the partial derivative of z with respect to x, imagine the y's are constant then. So this is really y squared e to the xy squared. Just for the same reason that I bring the 7 down here. So it's e to the 7x times 7 because 7 is the derivative of 7x. This is e to the xy squared times the derivative of xy squared, but y squared is just some constant. So it's y squared in front, just like it was for the 7 here. All right, now what about the derivative of z with respect to y? Okay, well again, the derivative of e to the xy squared is going to be e to the xy squared. And the derivative of this bit with respect to y, so you imagine the x is constant, like 3. What would you do? Well, you'd make it 3 times 2y. So it would be times x times 2y. In other words, it's 2xy e to the xy squared. All right, let's see. Well, I think the derivative with respect to x is going to be pretty easy on this one, because there's only one x in the whole problem. So the derivative of z with respect to x would be y cubed times, the derivative of cosine is negative sine, leave the xy alone, but then because of chain rule, if this was like 4x, you'd then multiply by 4, but it's yx, so then you multiply by y. So let me do a little recall over here. If you have the cosine of 4x, and you want to take the derivative of that, that's negative 4 sine of 4x. Exactly. It's just 4, quote unquote, for us is y. Y is a constant. So instead of cosine of xy, you take the derivative of that, it'll be negative sine of xy times y instead of 4, which would be negative y to the 4th sine of xy. All right, now the other one's going to be more difficult because we're going to have to use product rule. Because there's one function, y cubed, times another function, cosine of xy. Okay, so let's start with the y cubed. The derivative of y cubed is 3y squared. So I'll put 3y squared there. And then the derivative of, or excuse me, and then leave the cosine of xy alone. So I'm just going to write it, cosine of xy here, because I'm not doing anything to it. Plus, right, because there's two functions multiplied, so I'm using product rule. Derivative of the green, leave the other alone. Plus, now I want the derivative of the cosine of xy, leaving x as a constant. So that would be negative sine of xy times x. Same reason as above. Right? Same reason as right here, except you're leaving x as a constant, not y as a constant. So it's multiplied by x. So same reason as right up here. All right, and then we leave the y cubed alone. So that would be 3y squared cosine of xy minus xy cubed times the sine of xy. All right, now what about this one? Well, me personally, I learned in Calculus 1 never to leave a square root when you're trying to take a derivative. So I'm going to rewrite this. This is t squared times rs plus rt to the 1/2. So I want to find gr and gt. So gr. of RST. In other words, it's the partial derivative of G with respect to R. Okay, well, let's see here. I have this whole thing in here. The R's are inside of it. So I'm going to write my T squared times, and then if I want to take the derivative of this part, I would do 1/2 RS plus RT to the negative 1/2 times, now because of chain rule, I would need to take the derivative of the inner part right here. So from chain rule, the derivative of RS is S, and the derivative of RT is T. Again, because they're assumed to be constants. Like imagine this was, I don't know, 2R plus 7R. Well, then it'd be 2 plus 7. Simple as that, right? So that's what you have over here. So this is happening because of chain rule. Okay, so then let's simplify that just a little bit. So that's T squared times S plus T, because those are both in the numerator. In the denominator, you have a 2, and then you have a square root of RS plus RT. That would be the partial derivative. And they asked us for GT also, so let's find that. So that's the partial derivative of G with respect to T, so that leaves R and S as if they were constants. Okay, so, this is going to be tougher. I'm going to need product rule for this because I have a function of T here and I have another function of T here. So let's start with the T squared. The derivative of T squared is 2T. And then I would leave the RS plus RT to the 1/2. Then plus, now I leave the T squared alone, and then I want the derivative of the next part. So it'd be 1/2, and then RS plus RT to the negative 1/2, right? So we're bringing the power down. Oop, here it is. Bring the power down, leave the inner part alone, negative 1/2. And then because of chain rule, well, the derivative of RS is 0 because those are both constants as far as T is concerned. So 0 plus R. All right, just cleaning that up a little bit. That's 2T square root of RS plus RT. And then this is R and a T squared. So T squared R over 2 square root of RS plus RT. Now I forgot how to show this to you, but it's super easy to find the derivative with Maple. So you can always use Maple to back up your findings. So I did this for all these examples, but I named this function G5 because it's example 5. So I typed in what it was, and there it is, and it's showing it to me. And then I just say, find the differentiation. Differentiation, of course, difference quotient derivative. So take the derivative of that function, comma, with respect to R. And sure enough, it does. And then here's T, and that was what we just came up with. And it didn't ask for it, but there's S in case you want to know, right there. It's as easy as that. I actually did it for all these examples, so you can see I named a function, said take the derivative of it with respect to X or derivative of it with respect to Y. So the DIFF command does it. You can also use the deltas. The deltas you get from your palette. They're over here in the Greek symbols. So you're looking for the deltas. I just don't remember where they are. Actually, I was wrong. They're not there. They're in the calculus palette. It's up here. So in the calculus palette, take the derivative with respect to X. That's actually the second derivative. And we'll talk about those in just a little bit. Okay, so that's how to use Maple to find those derivatives. Me personally, I actually like the diff command a lot. I think it's kind of easy to work with and easier sometimes even than the palette.